The first step is to simulate the air cushion itself. This is achieved using spring elements and an additional airflow force. The pilot's weight shift, controlled by the player's inputs, acts on the hovercraft and simulates a different weight distribution. This allows the hovercraft to move and turn in all four directions without having to control the main rotor. The plan is to implement all primary controls with 4 input axes. 2 axes for the pilot's movements and the other 2 axes for the main thrust of the tail rotor and the rudder. The physical simulation includes mass bodies that are intended to simulate weight but have no other influence. These are divided into 5 main masses: the main chassis, front engine, rear engine, tail rotor assembly, and the pilot himself, whose mass can be changed in the game. In addition, there is a suspension system designed to simulate air suspension. There are 8 spring elements, each consisting of a collision sphere and a damper element connected to the main chassis. These simulate typical air suspension. This simulates smooth suspension and a constant distance from the ground in order to follow the terrain surface more realistically. The numbers indicate the height reached by the air skirt in the respective area. To see how it works and what effects the setup has, let's take a look at an example geometry. The geometry is responsible for collisions with the ground. Here we see the distances to the ground. The skirt of the air cushion is not yet deformed. However, the aim is to simulate contact with the ground through deformation. Changing the position of the pilot changes the weight distribution and thus tilts the entire hovercraft. This continues until the point where areas of the air skirt no longer seal. This reduces the overall air pressure under the air cushion and the entire hovercraft sinks down slightly. This movement is subtle, but it supports the overall impression. The air cushion vehicle reacts to the pilot's individual movements in all axes. The reduction in air pressure is achieved by reducing the strength of the individual spring elements. This reduction is calculated based on the size of the gap between the ground and the air skirt. At the moment, this goes so far that the chassis touches the ground. In addition to the spring elements, an additional force is implemented that mimics the behavior of the airflow under the air cushion. This is illustrated by the purple arrow. The pilot's movements change the direction of the force, imitating the airflow at their respective points. This airflow is primarily responsible for the movements without the use of the main rotor. Among other things, this enables rotation without the use of the rudder. In addition to the 2 buoyancy forces, which are the spring elements designed to simulate air suspension and the buoyancy force, a third force relevant to the air skirt is also simulated: friction. This is simulated by 6 independently calculated forces. The strength of the individual forces is defined by the distance to the ground. The closer the respective point is to the ground, the more the air skirt presses down on the ground there and generates more friction. The direction of the force is defined by the direction of movement of the individual points. These forces are not calculated for every image and therefore require less processor power. The movement of the pilot changes the contact pressure of the air cushion on the different sides. The arrow on the left is longer and presses harder there than on the other side. When I move the entire hovercraft in one direction, all arrows point in the same direction and only the strength varies. It gets interesting when the entire hovercraft rotates around its z-axis. Then the forces of the individual points act in different directions and thus also stop rotation due to differently acting frictional forces. This slows down not only the movement in one direction but also the rotation. The strength of the individual forces is not yet balanced in prototyping.